So let's add a couple of more processes that have been involved in the evolution of carbon cycle through Earth's history and regulation of climate. So we have to basically balance observed estimates of oxygen, carbon burial rates, weathering rates, temperatures, and so on, to see how they have played out together. And this is this particular podcast is on just looking at iron, sulfur, and how their oxidation or deposition plays with the carbon cycle regulation. And there are two good examples. This one is from the time when the first jump in oxygen happened. So what are we looking at? This is the Archean Proterozoic carbon and sulfur isotopic data. So going from 3 billion to 1.5 billion years ago. The Loma-Gundi event refers to the interval of highly positive delta C13 values shown in this black band between 2.3 gigayears and 2 gigayears here. The preceding collapse in the range of delta 33S values in red and gray indicates the increase in atmospheric O2 levels from the vanishing Archean levels for the first time. So the oxygen was very low, free oxygen in the atmosphere was very low. The first jump happened around 2.4 million years ago. So what are we trying to do? Basically, the big evidence we have to explain is that there is this increased delta C13 in parts per thousand around this time when oxygen is also shown to be increasing in the atmosphere. So organic carbon burial, when delta C13 is high, it basically means there is a large fractionation which happens because of biological activities, and we know that there was no land plants at this time, so it's a ocean photosynthesis process. And large organic carbon burial also means that the CO2 was taken away from the atmosphere, but to explain the temperatures that were observed at the time, you have to then supply the right amount of CO2 so that the you can match the weathering rates, removed carbon by organic carbon burial, and the temperature that was observed. Of course, oxygen is an addition here. So the main explanation is that the oxygen levels can oxidize iron and sulfur, basically things like siderite, which are highly oxidizable. So if the ocean is anoxic, then the iron can remain in soluble form, but if oxygen rises beyond a threshold, then it becomes insoluble and precipitates out, and the ocean crust and the land crust are also affected by the exposed iron and its oxidation. So sulfur here is the collapse seen here just before the rise in carbon burial is an indication that the increased oxygen that was observed here led to large oxidation of siderite and increased the CO2, which allowed the organic burial of carbon to be compensated for, so that the weathering rates, temperatures, and carbon levels together with oxygen can be explained. Okay, so that's one strong coupling between iron, sulfur, oxygen, and carbon. The other example is this one, looking at CO2 released in 10 to the 8 moles, O2 consumed in 10 to the 8 moles, and this is looking at 15 million years ago. So remember, we looked at the mountain building, especially the Himalayas, and the drop in CO2 and temperature from about 50 million years ago to about the end of last ice age, and then Holocene and global warming have changed the trajectory. But nonetheless, if you consider the amount of CO2 that would be drawn down by weathering of these mountain building and the temperature changes, you need to find a source of additional CO2 as well. And this paper looked at that. So it is looking at various levels of oxygen in terms of percentage of the atmosphere. We are at 21% today. The Phanerozoic maximum is estimated at 35%, and it dropped to 30% and 25%, or down to 21% in terms of what was present in the last 15 million years. In other words, the range of oxygen in the atmosphere supported by this paper here goes all the way from 35% in the Phanerozoic to 21% in the modern. So the PO2 at 15 million years ago is what we are trying to use to explain CO2 levels and oxygen consumptions and the temperature changes, together with the weathering rates that were increased by mountain building, right? So trade-off between CO2 release and O2 consumption as a result of sulfide oxidation. Dashed horizontal lines represent CO2 release required to fully compensate for a 10%, 25% and 50% increase in continental silicate weathering that occurred linearly over the past 15 million years, directly related to alpine and Himalayan mountain building. This assumes a modern flux of 3.5 times 10 to the 18 moles per million years. The 25% increase corresponds to the increase predicted by the mass balance model of this paper in reference 10 of this paper cited here, and implies PO2 at 15 million years ago to be about 25% here. Estimate for the maximum possible atmospheric O2 content of 25% is at odds with modeling and experimental evidence for higher maximum O2 content. So there are still issues, and mostly we are taking available geochemical evidence and we're trying to fit a model, and multiple models are built obviously, and there are focused on different aspects of the oxygen weathering, CO2 in the atmosphere, temperature, and they can come up with different estimates. The solid line shows the ratio of CO2 released to O2 consumption for sulfide oxidation. So without going too much into the details of the paper, which you can read if you want, the main point I would want to convey here is that the oxygen consumption and sulfide oxidation are required on many occasions in Earth's history to explain the CO2 that would be required to explain the temperature. So CO2 evolution, temperature regulation are affected by weathering rates, oxygen levels, and sulfide and iron oxidations. So all those constraints are basically indicators that iron and sulfur have been key players in carbon dioxide regulation as well. Here is another example. We are looking here at the dissolved silica concentration and reverse weathering rate. What are we doing? We are going back to reverse weathering through Earth's history to try to understand its role on carbon regulation on geologic timescales as well. So we are looking at Precambrian profiles where silica supplied by weathering was high in the ocean because biogenic silica precipitation was not happening. So the Precambrian photosynthetic levels and generally land vegetation, everything else was lower in terms of ocean species that could form silica shells and rain it out and take it out of the system. Remember that reverse weathering depends on alkalinity to silica ratio, and there are details about how carbonate precipitation consumes CO2 in the atmosphere, alkalinity in the carbonate alkalinity in the ocean, whereas reverse weathering only consumes alkalinity. So in the Phanerozoic, where life was beginning to life was beginning to explode, especially starting with the Cambrian, where you had a huge explosion of some 25 million species, and oxygen was already high enough to allow large multicellular species. You had much lower silica, because you had lots of biogenic silica precipitation happening once the species evolved, which removed the or changed the alkalinity to silica ratio and made it possible for reverse weathering to become much less. So you can see the reverse weathering rate here is much larger in the Precambrian, with the e-folding depth shown here, whereas the profile for the Phanerozoic is remarkably different. It is higher, very close to the sediment-ocean interface, but quickly drops off with depth in the sediments, which is shown here in centimeters. Okay, so this again shows the reverse weathering regulation of carbon dioxide through Earth history. And you have to always remember these are longer time scales, so we can ignore the details of the carbon cycle within the ocean and just consider atmosphere and ocean CO2 regulation and climate regulation at very long time scales. Okay, so finally we can look at this cartoon summarizing modern and Precambrian carbon cycle sources and sinks. Elevated rates of degassing have been predicted from geophysical models for the Precambrian relative to the modern. So Precambrian is when the there was just there were no bilateral symmetry, and the most of the species that existed were like jellyfish from the Ediacaran and so on. So they had radial symmetry. This gene called the homeobox gene had not developed, had not evolved. Of course, there were no land colonization of photosynthesizers yet, which came later into the Cambrian, and the general increase in number of species itself exploded in the Cambrian and into the Phanerozoic. Phanerozoic is visible life, Proterozoic is early life, in case you didn't already know that. Okay, so elevated rates of degassing have been predicted from geophysical models for the Precambrian relative to the modern, and on this basis carbonate export tied to silicate weathering must be proportionally larger. So again, we are using multiple constraints here to compare different periods. Higher dissolved silica and iron levels that are hallmark features of Precambrian, higher dissolved silica and iron levels that are hallmark features of the Precambrian, when silica rain precipitation because of species was not happening, so reverse weathering was higher. This gave rise to conditions that favored enhanced rates of reverse weathering and dampened marine weathering rates. By this framework, it follows that the ratio of terrestrial to marine silicate weathering rates would have been higher. So the terrestrial, most of the weathering was happening on land. Marine silicate weathering was damped, basically because reverse weathering was putting the CO2 back, and silica was alkalinity was being consumed. So this is what is being shown here in terms of the reverse weathering rates over time. So we are looking here at Precambrian magnitude and modern magnitude. So the metamorphic and volcanic degassing models suggest, based on all these constraints, that it was higher during the Precambrian and lower during the modern. There is also the magmatic degassing going on. This is what we are talking about. Marine weathering is higher now than it would have been in the Precambrian, because reverse weathering was higher in the Precambrian compared to the modern periods. And the carbonate and organic carbon export, the CH2O is the basic carbohydrate molecule, would have been higher during the Precambrian to the extent that there were photosynthesizers living in the ocean. And terrestrial weathering was higher than today, because marine weathering was relatively lower during the Precambrian, and terrestrial weathering was higher. So it sounds complicated, but we are basically juggling with a few pieces of information for CO2 levels, weathering rates, reverse weathering rates, oxygen levels, iron and sulfide and carbon burial rates, and so on. So we have to balance all these things together to come up with a story, and there are still many uncertainties with each of these components, and we use models to fit the story together over time, and lots of assumptions are involved, so one has to be careful about that as well. But we will come back and look at the future of carbon a little bit, which already is recorded in the podcast in the earlier sections from Archer's book, but we will revisit some of the issues. Okay,